Hello viewers and welcome to the e-learning classroom. So today we'll be looking at KCSE 2021 paper 1. So let's go straight to the questions. So section A, 25 marks. Question 1. Figure 1 shows part of the thimble scale of a screw gauge with 50 divisions. Figure 1 shows part of the thimble scale of a screw gauge with 50 divisions. On the diagram, draw the sleeve scale to show a reading of 3.87 millimeters. So we are drawing to indicate 3.87 millimeters. So you can see the answer there. So that means for the thimble part, we already have 37, because you can see we have that 5, that 6, 37. That's the one coinciding with the sleeve. So that 7, and that means now you require 3.5. So that is why we have 3. Before thimble, we have 3.5 on the lower side. Although that half can also be on the upper side. So that is 3.5 plus 0.37, which gives you 3.87. Question 2. Figure 2 shows a siphon used to empty a tank. Figure 2 shows a siphon used to empty a tank. In order to start the siphon, state why A, it must be full of liquid. Why it must be full of liquid? The answer is for the liquid to be pulled down by cohesive forces. In other words, you are filling it with the liquid so that when the liquid starts flowing, it will be pulled down together by cohesive forces. B, and X must be below the level of liquid in the tank, and X must be below the level of the liquid in the tank. So for X to have a lower pressure than liquid in the tank, or to create a pressure difference. In other words, we are saying the reason why X is below the water in the tank is so that the atmospheric pressure acting on the liquid of the tank can be greater than pressure at point X. Remember, pressure depends with depth. So that means the liquid on the tank will have high atmospheric pressure than the pressure acting on side X. That's why now we are saying it will create a pressure difference. Question 3. Figure 3A shows a horizontal tube consisting here trapped by a mercury thread of length 5 centimeters. The length of the enclosed hair column is 7.5 centimeters. The atmospheric pressure is 76 centimeters of mercury. So you can see the two tubes with a mercury thread. There is a trapped hair. The tube is then turned vertically with its mouth facing downwards as shown in figure 3B. Question A, determine the length of the air column. Determine the length of the air column, that is length L. So you can see initially the tube is horizontal, then it is vertical. So when it is horizontal, you realize that the reason why the mercury thread is not coming out or returning inwards is because the atmospheric pressure has been balanced by the pressure of the trapped gas, and that's why now pressure 1 is the atmospheric. In other words, this is a Boyle's law where we are relating pressure and volume. So that means P1 V1 equals P2 V2, or pressure 1 times volume 1 equals pressure 2 times volume 1. So pressure 1 is the atmospheric, because atmospheric is balancing the pressure of the trapped gas. That means it will be 76 times 7.5 is equal to pressure 2 is atmospheric minus liquid pressure, that is 76 minus 5. Remember, one of the units of pressure is centimeters of mercury. So we are working with centimeters of mercury direct. So 76 minus 5, that is the pressure 2, then multiplied by volume. For the volume, again, we are treating the height of the trapped liquid as the volume. So 76 minus 5 times L. So L becomes 8.028 centimeters. B, state the reason why. So question B is saying state the reason why the mercury thread did not fall out in figure 3B. State the reason why the mercury thread did not fall out in figure 3B. So there are two reasons there, or maybe any alternative you can give. The first alternative, the atmospheric pressure is greater than the pressure due to the mercury thread. In other words, the mercury thread pressure is acting downwards, whereas atmospheric is acting upwards. So it means atmospheric is greater than the liquid pressure only. Remember, we are ignoring the pressure due to trapped gas. So we are saying atmospheric is greater than liquid alone. B, another way, the atmospheric pressure is equal to the sum of pressure due to the trapped air and the mercury thread pressure combined. In other words, the atmospheric, which is acting upwards, is equal to pressure due to liquid acting downwards and pressure due to trapped air also acting downwards. So the two are balanced. That's why now the liquid is not falling out. So let's go to question 4. In a physics experiment, a student filled a burette with water up to a level of 15 ml. The student ran out 3 drops of water, each of volume 2 centimeter cubed, from the burette into a beaker. Determine the final reading of the burette. So we have a burette, initial reading is 15 ml. Then the student is running out 3 drops of water, each of volume 2 centimeter cubed, into another beaker. Then you are trying to determine the final reading. So first of all, let's get the volume of drops that ran out. So volume of drops is 3 times 2, which is 6 centimeter cubed. Then the final reading is 15 plus 6, which gives you 21 centimeter cubed. Remember, when you remove something from a burette, you normally add the reading. Reason being, at the top the reading is 0, and then the bottom the reading is 50. That means the more you are removing some liquid, the higher the reading you get. State 2 factors that affect the angular velocity of a body moving in a circular path. 2 factors that affect the angular velocity of a body moving in a circular path. So number 1, radius of the orbit, linear velocity of the body, the periodic time or frequency of the oscillations. These are the 3 factors that affect angular velocity. Question 6. Figure 4 shows 2 capillary tubes X and Y of different diameters dipped in mercury. Figure 4 shows 2 capillary tubes X and Y of different diameters dipped in mercury. Complete the diagram to show the meniscus in Y. So you can see the level in Y. It's below the level in the beaker, but above the one in tube X. Then question 7. In an experiment, a drop of black ink is introduced at the bottom of a container filled with water. In an experiment, a drop of black ink is introduced at the bottom of a container filled with water. It is observed that the water gradually turns black. State the effect on the observation when the experiment is carried out using water at a lower temperature. Water at a lower temperature, then you're observing what is happening. So the rate at which water turns black decreases. The rate at which water turns black decreases. In other words, the rate of diffusion decreases. Question 8. Figure 5 shows 2 identical springs arranged side by side and supporting a weight of 50 Newton. When the same weight is supported by one of the springs above, it produces an extension of 1 centimeter. Determine the effective spring constant of the arrangement in figures. So you are told already if 50 Newton is supported by only one spring, then the extension is 1 centimeter. That means we can get the spring constant of one spring, which is a force of extension, 50/1, which gives 50 Newton per centimeter. Then we have spring constant of the two springs combined. Remember, the two are in parallel, so when they're in parallel, we normally multiply because the spring constant increases. So it will be 2 times the spring constant of one spring, which is 100 Newton per centimeter. Question 9. On the axis provided, sketch a graph of density against temperature for water between 0 degrees Celsius and 10 degrees Celsius. So we have the graph of density against temperature. So we know they are testing the anomalous behavior of water. So that means from 0 to 4, when you heat water from 0 degrees to 4 degrees, it normally contracts. When you heat water from 0 to 4, it contracts, and that means density is increasing. And then when you heat water from 4 to 10, you realize it normally expands, and that means now that the density decreases. In other words, 0 to 4, you can see the graph, density is increasing, and then 4 to 10, it is decreasing. The key thing is that at 4, it is curved. It's a curve and not a triangle, so you must be sure of the curve there. Let's go to question 10. State the reason why a student climbing a hill tends to bend forward. State the reason why a student climbing a hill tends to bend forward. So, one, the reason is in order to maintain stability to avoid falling. In order to maintain stability or avoid falling, or you can also say, so that the line of action of weight still passes through the base area of his feet, hence maintaining stability. So that the line of action of weight still passes through the base area of his feet, hence maintaining stability. Question 11. Figure 6 shows a graph of temperature against time for a pure molten substance undergoing cooling. Figure 6 shows a graph of temperature against time for a pure molten substance undergoing cooling. We have temperature against time. Explain what happens to the substance in region BC. So if you look at the temperature, it is dropping from A to B, then B to C it is constant. That means the substance is now solidifying. In other words, that is the freezing point. So in other words, BC, the molten substance freezes or solidifies since it is losing latent heat of fusion. In other words, you've got to give the two answers so that you get the 2 marks. The pure molten substance solidifies since it is losing latent heat of fusion. So let's go to question 12. Figure 7 shows a uniform rod AB 2 meters long and of mass 1 kilogram. It is pivoted 0.5 meters from end A and balanced horizontally by a string attached 0.1 meter from end B. So you can see the diagram there. We have A, we have B, 0.5 meters, we have 0.1 meters. Then it is the whole thing is 2 meters long. Determine the tension in the string. Take G equals 10 Newton per kilogram. So we know because the system is in equilibrium, force 1d1 equals force 2d2. In other words, the sum of clockwise moment is equals to the sum of anticlockwise moment, and that means that we have force 1 is the weight of this uniform rod, which is acting through the COG. In other words, through the 1 meter mark, because the whole thing is 2 meters. the rod is 2 meters, so the weight is acting through 1 meter. So 1 kilogram is, in terms of weight, is 10 newton. So we have 10 times 0.5, because you will say, remember, you will say weight, the point where the weight is acting is 1 meter. 1 meter minus 0.5, 1 minus 0.5, which gives you 0.5 meters. So 10 times 0.5 equals tension on the string times 1.4. 1.4 is the distance, 2 meters minus 0.5 and 0.1. 2 meters minus 0.5 and 0.1, which gives you 1.4. So that's how you get the tension, which is 3.571 Newton. Question 13. Figure 8 shows two pieces of ice A and B trapped using wire gauze in a large beaker containing water. You can see the beaker containing water. We have source of heat. We have ice A and B. It is applied at the center of the base of the beaker as shown. State the reason why B melted earlier than A. Why has B melted earlier than A? So you realize that heated water molecules expand, become less dense and rise. Hence, more heat reaches B than A. In other words, we love convection currents, whereby now when you are heating the water, normally expands, become less dense and rises. That means now the more heat will be reaching B compared to A. Let's go to question 14. Figure 9 shows a folded piece of paper. A stream of air is blown underneath the paper. You have a paper there, then we have air, stream of air. Explain why the paper collapses. Explain why the paper collapses. So the stream of moving air underneath the paper lowers the pressure below the paper. Hence, the greater atmospheric pressure above the paper causes the paper to collapse. In other words, remember, this is Bernoulli's effect, whereby now they are comparing pressure below the paper and above the paper. So, and that's why now we are saying, due to the stream of moving air, pressure below the paper lowers below the atmospheric, and therefore the great atmospheric above it is now what makes the paper to fold. So that is the end of section A. So we go now to section B. This one has got 55 marks. So question 15A. Figure 10 shows a wooden block of volume 90 centimeter cubed floating with a third of its body submerged in water of a density 1 gram per cubic centimeter. So we have a wooden block, volume 90 centimeter cubed. A third of its weight is submerged. Determine the weight of the block. So because this block is floating, you realize now that we apply the law of flotation, whereby now we can say the weight of the block must be equal to the half thrust. In other words, downward force is equal to upward force. The weight is equal to half thrust, and that means now weight will be given by rho Vg, which is rho is 1,000, density of the liquid. Volume of liquid displaced is a third of 90 centimeter cubed, but in SI units, then G is 10. So that is a third of the volume, rho Vg, density of the liquid times volume of liquid displaced times 10. That is applying the law of flotation, because we are saying downward force is equal to the upward force. In other words, weight equals to up thrust. That gives you weight being 0.3 Newton, which is also the same as the half thrust. Roman 2, the weight of the metal block that can be placed onto the block so that its top surface is on the same level as the water surface. In other words, to submerge this block completely, how much more weight is needed above? So in other words, we need to know for the remaining unsunk part, what is the upthrust that will be experienced when you submerged it, the remaining part. So in other words, weight equals the the weight needed to be added on top is the extra half thrust, which is rho Vg, V being the remaining unsunk volume. Then you say 1,000 times 2/3 of, remember when you removed a third of its volume, then 2/3 is floating, so you are now submerging 2/3, then G is 10, then you get your answer is 0.6 Newton. Let's go to question B. Figure 11 shows a solid metal suspended in oil using a thread. Figure 11 shows a solid metal suspended in oil using a thread. Other than up thrust, list 2 other forces acting on the sphere. Other than up thrust. So we know the other 2 forces include, of course, anytime you are trying to name the forces acting, the first force to name is always the weight, because weight must always be there. So the first force is the weight of the sphere and its contents. Then the second force is tension on the string. Question Roman 2, B Roman 2. The oil is carefully and gradually drawn from the beaker. State the effect on each of the 2 forces when you remove some oil from the beaker. When you remove some oil, that means weight does not change, because remember weight is dependent on mass. We say weight is mg, mass times pull of gravity. That means weight does not change because mass does not change. From the next part on tension is that tension will increase, and the reason why tension increases is that upthrust is decreasing. Remember, upthrust depends on volume of liquid displaced or volume of oil displaced. That means when you remove more oil, it means volume of oil displaced is reducing, and that means now that upthrust reduces. In other words, the upward force reduces, therefore tension becomes greater, because tension is given by weight minus upthrust. So the tension increases. Let's go to question 16a. Question 16a. Define the term specific latent heat of fusion. Define the term specific latent heat of fusion. So it is the quantity of heat required to change the state of a substance from solid to liquid state without changing temperature. Quantity of heat required to change the state of a substance from solid to liquid state without changing temperature. Let's go to question B, 16b. Ice of mass 5 gram at a temperature of -10 degrees is immersed into 10.5 gram of hot water at 100 degrees Celsius in a container of negligible heat capacity. That means we have a container having hot water at 100 degrees, and now you are submerging ice at -10. All the ice melts and the final temperature of the mixture is 40 degrees Celsius. Assuming there are no heat losses to the surrounding and taking specific latent heat of fusion of ices, LF, into bracket specific heat of water, 4200 joule per kilogram per Kelvin, and a specific heat capacity of ice, 2100 joule per kilogram per Kelvin. Determine the heat lost by the water. There is the hot water. Remember, the hot water is at 100, and then the final temperature is 40. That means the heat lost by the water is given by MC, change in temperature, MC theta, or MC change in temperature. In other words, mass of the hot water is 10.5 gram, but in SI units 0.0105 kilogram. Specific heat capacity of water is 4200. Change in temperature is 100 minus 40. So that one gives 2646 joule, 2646 joule. Roman 2, heat gained by ice from -10 to 0. Heat gained by ice from -10 to 0. That means because there's a change in temperature, heat will be given by mc theta again for ice. So it is mass of ice is 5 grams, so it will be 0.005 in kilograms. Heat capacity, specific heat capacity 2100. Change in temperature is 0 minus -10. 0 minus -10, and that gives you 105 joule. Roman 3, heat required to melt the ice in terms of LF. It required to melt the ice in terms of LF. So that means it will be given by MLF. That means the mass of the ice is 0.005 kilogram. That one's 5 gram in SI units times LF, which gives you 0.005 LF. Roman 4, heat gained by the melted ice, meaning after it has melted now, that means now from 0 degrees up to 40, which is the final temperature of the mixture. Remember, when ice melts now, it becomes water. After melting, it becomes water. That means it will be given by mc theta. Mass is still 5 gram, but in SI units. Specific, after it has melted, is now water, so specific is now 4200. Change in temperature 40 minus 0, and that gives you 840 joule. Remember, ice is gaining heat in 3 stages, from -10 to 0, at 0, which is the melting point, then 0 to 40, which is the final temperature of the mixture. Lastly, Roman 5, specific latent heat of fusion, in other words, the value of LF. We know heat lost by the hot water will be equal to heat gained by ice up to 40 degrees. In other words, heat lost is Roman 1, which is 2646 joule. Heat gained is the heat gained in the 3 stages, that is Roman 2, Roman 3, and Roman 4. So we are adding 105 plus 0.005 LF plus 8400, and when you solve that, you get LF equals latent heat of fusion of water. Specific latent heat of fusion is 340-200 joule per kilogram. That is the specific latent heat of fusion of ice. Let's go straight to question 17. Figure 12 shows hydraulic lift system. The radius of the small piston is 5.64 centimeters, while that of the larger piston is 14.24 centimeters. The piston is operated using a lever. A force of 100 Newton is applied to the lever. Determine the... So you can first see the diagram. So that means we have a lever and we have hydraulic lift. These are 2 systems combined. You can see the effort applied, 100 Newton. Radius of the larger piston, 14.24 centimeters. Radius of the smaller piston, 5.64 centimeters. And then you are told to determine the A, pressure exerted by the smaller piston. That means first we need to get the force acting on the small piston. The force acting on the small piston, whose radius is 5.64 centimeter. So that means force 1d1 equals force 2d2. We apply the principle of moments for the lever. So 100 times the pivot is at the hinge. So 100 times the distance, which is 2 meters, that is 1.6 plus 0.4. 100 times 2 meters is equal to force 2, which is now acting through the piston. The downward force acting through the piston, force 2, times distance from pivot is 0.4 meters, Distance from pivot is 0.4 meters, and that gives you force 2 is 500 Newton. 500 Newton, that's force 2 on the smaller piston. Then we know pressure is force divided by area. But in that case, we still don't have area because we are given the radius is 5.64 centimeters. So we first get the area. Area of the piston is given by pi r squared. So 22/7 times 0.0564 squared, which gives you 0.0099993 meter squared. Then pressure is our force of area. So the force is 500 and we have the area down there. So you divide and then you get the answer for pressure is 50,000 and that 3.61 Newton per square meter. Let's go to part B. Load that can be lifted. The load that can be lifted. So we are considering the hydraulic lift alone. So we know load is given by pressure times area. Remember, this thing is applying the Pascal's principle. In other words, the pressure acting on the small piston is equal to the pressure acting on the larger piston. That means pressure on side A and side B is the same. In other words, pressure on the right and left sides are all the same. So that means because you have pressure on the left side, which is 50,033.61, because it's the same every side, and then you have the area you can get because you have the radius is 14.24. That means now pressure is load. In other words, force is pressure times area. Load is the same as force, pressure times area, and then you multiply. Now the area is pi r squared. So you first get the area and then you multiply by pressure, which gives you 3,187 Newton. Part C, mechanical advantage of the system. Mechanical advantage of the system. Remember, this is a combined system of a lever and hydraulic lift. So mechanical advantage will be the load over effort. Load is the entire load that can be lifted, which is that 187 Newton. Effort is what you applied to the machine, which is 100 Newton. And when you divide, you get that 1.87. Remember, it's a combined system. So we are working with the two systems as one. So that's why we are saying now you take the effort, which is the force applied to the machine, divided by load. Load is the force exerted by the machine. So that means that 187 divided by 100. That is our load over effort. So let's go now to the very last question, 18A. 18A, a bus moving initially at 20 meters per second decelerates uniformly at 2 meters per square second. A bus moving initially at a velocity of 20 meters per second decelerates uniformly at 2 meters per square second. Roman 1, determine the time taken for the bus to come to a stop. Time taken for the bus to come to a stop. That means the final velocity is 0. Because stop means final velocity is 0. Initial we are given is 20. We also have acceleration. So we apply the Newton's first equation. Remember, as long as there is a variation of velocity, in other words, if there is acceleration or deceleration, then the Newton's equations of motion will work. So that means V equals U plus 80. Final is 0. Initial is 20. Acceleration is 2. That is 2t. But in this case now, acceleration is negative. So acceleration is negative 2t because it is a deceleration. So deceleration of 2, that means acceleration is negative, so it is negative 2t. So acceleration is negative 2. Then when you bring negative 2 the other side, you get time equals 10 seconds. Roman 2, sketch the velocity time graph for the motion of the bus up to the time it is stopped. Velocity time graph up to the time it is stopped. So for that case, because acceleration is a constant, which is negative 2 meters per second, that means now the slope will be constant. You know, the slope of velocity time graph represents acceleration. Slope represents acceleration because it is change in velocity divided by change in time, and that means the slope will be constant, and the constant slope means a straight line. But in that case now it is going down. It is going down, meaning it has a negative gradient, meaning acceleration is negative. In other words, velocity is dropping with time up to 0. Roman 3, use the graph to determine the distance moved by the bus before stopping. Distance and the velocity time graph. We know velocity time graphs, distance normally is given by the area under the graph. That means you simply find the area under the graph, which is half base times height, half 10 times 20, which gives you 100 meters. 100 meters. Let's go to question B. A car of mass 100 kilogram traveling at a constant velocity of 40 meters per second. A car of mass 100 kilogram, 1000, sorry, a car of mass 1000 kilogram traveling at a constant velocity of 40 meters per second collides with a stationary metal block of mass 800 kilogram. A car of mass 1000 kilogram traveling at a constant velocity of 40 meters per second collides with a stationary metal block of mass 800 kilogram. The impact takes 3 seconds before the two move together. Determine the impulsive force. We have a car colliding with a metal block which is stationary. The car is moving and the two stick together. That means this is inelastic collision. It's an inelastic kind of collision. Then you are trying to determine the impulsive force. We know impulsive force is given by change in momentum divided by change in time. Change in momentum divided by change in time. That is according to Newton's second law. The Newton's second law of motion. In other words, change in momentum is the same as impulse then divided by time, or change in momentum divided by time. So first of all, we have the mass, which is 1000 kilogram. We also have the initial velocity, but we do not have the final velocity after collision. That means we'll start by getting final velocity after collision. So the sum of momentum before collision is equals to sum of momentum after collision, and because it is inelastic collision, we have the common velocity. So we work now the final velocity now, which is 22.22 meters per second. M1U1 is the initial momentum of the car. M2U2 is the initial momentum of the block, which is initially stationary. That's why initial momentum is 0. Then we have total mass times the common velocity, and that gives us a final velocity is 22.22 meters per second. But now when it comes to the impulsive force, for the change in momentum, we just pick on either the car or the block, the metal block. So when you are looking for change in momentum, because there is final momentum and initial momentum for each one of them, so you just pick any of them, but they should give you the same answer. So for example, now we have picked the metal block. Metal block, although you may also work with the car. So the initial momentum is 0 and the final momentum is mv 800 times 22.22. The 800 times 22.22 minus 0, which gives you, divided by 3, which gives you 59.26 Newton. And that's now that is the force, the impulsive force. Oh, lastly now question 19. Question 19. A State two conditions necessary for a body to be in equilibrium. 19a. State two conditions necessary for a body to be in equilibrium. So 1. The sum of clockwise moments about a point is equal to the sum of anticlockwise moments about the same point. The sum of clockwise moments about a point is equal to the sum of anticlockwise moments about the same point. Another condition, the sum of forces acting in one direction is equal to the sum of forces acting in the opposite direction. The sum of forces acting in one direction is equal to sum of forces acting in the opposite direction. For the second part, you may also say that the algebraic sum of forces is 0. Algebraic sum of forces. Remember, force is a vector quantity. 19b. Figure 13 shows a non-uniform log of hood AB of length 4 meters. Figure 13 shows a non-uniform log of hood AB of length 4 meters. The log is held horizontally by applying forces 80 Newton at end A and 120 Newton at end B. So we have 80 Newton in A and 120 Newton in B. We have reaction R. Determine Roman 1, the value of R. Remember, we said the sum of forces in one direction must be equal to the sum of forces in the opposite direction. That means you'll just add 120 plus 80, which gives you 200 Newton. Roman 2, the position of the center of gravity of the log from A to B. In other words, the position of COG from A to B. So force 1 D1 equals force 2 D2. Let's assume the pivot is at point X. So 120 times the distance. Let's say distance from 120 is X. So 120 times X, which is only the distance from side B and B. 120 times X equals 80 times. The full length is 4 meters. Then from 120 to pivot is X. So 80 times 4 minus X. So 120 times X equals 80 times 4 minus X. And that gives you X to be 1.6 meter. So X becomes 1.6 meter. Let's go to C. You are provided with the meter rule, a knife hinge, and a mass M1. You're provided with meter rule, knife hinge, and a mass M1. Describe how the position of the center of gravity of the meter rule can be determined using the knife hinge. Describe how the position of center of gravity of the meter rule can be determined using the knife hinge. In other words, how do you determine the position of COG using the meter rule and a knife? So place the meter rule on the knife hinge and adjust until it balances. Place the meter rule on the knife hinge and adjust until it balances. Mark the balancing point of the meter rule, which is the position of center of gravity. So the balancing point becomes the position of COG. That is the first thing, you balance the meter rule on the knife hinge until it balances. Then the balancing point becomes the position of COG. Roman 2, C Roman 2. Using the position of center of gravity determined in 19C Roman 1 and the mass M, describe how the mass M of the meter rule can be determined. How you can determine mass M of the meter rule. You remember you have another mass M1, but now you want to determine mass M of the meter rule. You already have a knife, a meter rule, and another extra mass M1. So Roman 1, the first point is suspend mass M1 on the meter rule and adjust the position of meter rule on knife hinge until it balances horizontally. You first suspend the mass M1 on the meter rule. Then you now adjust the level of meter rule until now it balances again. Remember, you have already marked the COG initially. So the second procedure, measure the distance d1 of the position of COG from the balancing point and the position of mass m1 from the balancing point. So you remember, now you already have a knife hinge, a meter rule balancing horizontally. We have mass m1 and the COG on the other side, so they are balancing the COG because weight of the meter rule acts through the COG, and mass m1, the weight of its mass through the point where it is. So we have two distances. Measure the distance d1 of position of COG from balancing point and position of mass m1 from the balancing point. Use the principle of moments to determine the weight W of the meter rule. In other words, principle of moments is F1 d1 equals F2 d2, or sum of clockwise moments is equal to the sum of anticlockwise moments. The mass of the meter rule, M, is given by weight over G. That is the weight of the meter rule, which you got in Roman 3, divided by 10G. Then you get the mass of the meter rule. Remember, if you sketch that diagram, you can be able to understand more on what we are saying in the first procedure. And also, it's important to know that a procedure must follow each other. The steps must follow each other because it must be workable and it must be very concise and straight to the point. So that is what was required in Physics Paper 1, 2021. It was a very simple paper. Though it was technical, so it required high level of understanding the questions. So that marks the end of today's session. Let's see you in the next video.